Section P4 talks about inverse functions. So we're going to verify that one function is the inverse of another function, determine whether a function has an inverse, and then develop properties of the 6 inverse trigonometric functions. So the first thing here with inverse functions, just that definition, brings in that composite of two functions. So if you have a function g and you're saying that it's the inverse of a different function f, then when you do the composite of f of g of x, it would simplify down to x. And if you do the composite of g of f of x, it would also simplify down to x. If they don't simplify down to x, then they're not going to be inverses. So just a few things for notation. Remember that if you see this f inverse of x, f inverse of x is not exponential, so it's not 1 over f of x. Okay, so an inverse doesn't mean reciprocal. It means the inverse, where you're switching your x and your y values. So a few important things about inverse functions. If g is the inverse of f, then f is the inverse of g. So you won't have one being the inverse of another and then not have it reciprocated. The domain of the inverse, so this is something to kind of keep in mind. If you want the domain of the inverse function, sometimes the easiest way to find the domain of the inverse is to go back to your original function and determine what the range of the original function is. And that comes because your x and your y values switch in inverses, which means that your domains and your ranges switch. Same thing, if you need the range of the inverse, it's going to be whatever the domain of the original function was. A function doesn't have to have an inverse, but when it does, the inverse is unique. So a function will only have an inverse. So f of x will have an inverse if f of x passes the horizontal line test. So if you could draw a horizontal line and it only crosses the function one time, then we know that the function would have an inverse. And you can think about an inverse as undoing what's been done by f. So first example, verifying inverses. If we want to show that the functions are inverses of each other, then what we need to show is that f of g of x will simplify down to be x, and that g of f of x will also simplify down to be x. So let's first start with f of g of x. So we're going to substitute g into f. So we'll have 2 times the cube root of x plus 1 over 2. That's being substituted in for this x cubed minus 1. So now if we simplify, the cube root and the cube will simplify, so you're left with 2 times x plus 1 over 2 minus 1. The 2's simplify, so you have x plus 1 minus 1, which gives you x. So f of g of x simplifies down to be x, but you also have to show that g of f of x does the same. So this time we're going to take the cube root, and then in for this x, we're going to substitute 2x cubed minus 1. And then we still have the plus 1 from right here, all over 2. So we have the cube root. The minus 1 plus 1 simplifies, so 2x cubed over 2. The 2's simplify, so we're left with the cube root of x cubed, which is just x. So that also simplifies down to x. So then we know that f and g are inverses of each other. With the existence of an inverse, this is what we talked about a little bit earlier, the idea that not every function has an inverse, and the way that you can test it is by graphing your function and determining if it passes the horizontal line. So if you notice with this parabola, if I were to draw a horizontal line, it would pass through twice. So because it passes through twice, this would not have an inverse. An inverse function. Because if you were to graph what the inverse would be, I guess we should define that, an inverse function. it'll have an inverse, but it just wouldn't be a function because the graph of the inverse would look something like this, right, which wouldn't actually be a function. So in example 2, which of the following has an inverse function? So what we're going to do is we're actually going to graph these equations. So the first one, if you were to graph x cubed minus 1, and you were to just draw a quick sketch of what that graph looks like. It crosses down here at -1, and it looks like this. Not a real steady line. And then you were also to graph x cubed minus x plus 1. If you were to sketch a graph of this one, this crosses at +1, and it looks more like this. It's not a great graph, but if you look at these two graphs, you'll notice that in graph B, if you were to draw a horizontal line through the graph, it would pass through that graph several times. So that means that we know that A has an inverse because it would never pass, the horizontal line would never pass through the graph more than once. So your guidelines for finding an inverse function, there's a couple ways. The book has us first changing our f of x into a y, and then it has us solve for x and then switching the x and the y. A lot of us, or a lot of you, will actually switch the x and the y first and then solve for y. Either way will work. Remember, though, that if our function started out with a name like f of x, then at the end we have to call it f inverse of x. We can't call it y. We can't rename it. And then sometimes we'll have to define the domain and the range, or the domain of the inverse. And remember, the domain of the inverse will just be whatever the range of that original function was. So in this example, finding the inverse function, so first we're going to change our f of x into a y. So y equals the square root of 2x minus 3. The book wants us to solve for x first. My guess is a lot of us will want to switch x and y. So let's switch x and y. So if we have x equals the square root of 2y minus 3, and then we're going to solve for y. So you're going to have to square both sides. And so then we'd have x squared plus 3 divided by 2 would equal y. And remember, our original function was f of x. So we would have to say the inverse is x squared plus 3 over 2. If you call it y, you're not actually talking about that same thing. It wouldn't be recognized on the AP test, and you would lose a point for like a mislabel. So make sure that you're going back and renaming using the actual original name of the function. And so then the other thing that we have to determine is, what is the domain of this? So the domain of this is sometimes the easiest way to find your domain is thinking about what would the range of this function be, right? And we know that the range of a square root function that hasn't been translated up or down is going to be 0 to infinity. And so that means that we know that our domain then will be 0 to infinity. So again, finding the domain of your inverse, you need to go back to the original function and look at the range of that original function. All right, and then we're getting into trig functions. So with trig functions, they don't, this book doesn't use the notation of like y equals the inverse sine of x. What you'll see instead is y equals arc sine of x. It means the same thing. Remember, when you're doing the inverse sine, you're really just asking yourself, if we had this right here, if we had to find the inverse sine of x, we would be saying, you're really just solving for like the sine of an angle measure equals x. So when you take the inverse sine of x, you're solving for an angle measure on that unit circle. So you're really just saying, when does the sine equal theta? So when when on that unit circle would your theta be, whatever that value is. And then something else you have to remember is that for your arc sine and your arc tangent, you have a restricted domain of negative pi over 2 to pi over 2. So you're at negative pi over 2 to pi over 2. So your answers have to fall in that domain. For your arc cosine, you're restricted from 0 to pi. Right? That's your 0 to pi. So remember, keep that in mind as we're working through these. Here's your graphs of your inverse trig functions. So if you have to graph anything with your inverse trig functions, it might be worth just referring back to this slide. And so here, if we just kind of go through and try to remember what we're doing with this. So when we have arc sine of negative 1/2, so I'm going to use a little bit more room here. So if we have arc sine of negative 1/2, we're asking ourselves, we're solving for an angle measure. So we're saying, when does the sine of theta equal negative 1/2? And remember, we're restricted from negative pi over 2 to pi over 2. So when does the sine, which is your y, equal negative 1/2? So we're right there, which would mean that our theta would have to be negative pi over 6. Okay, we couldn't use 11 pi over 6 because we're outside of that restricted domain. So for B, if we have arc cosine of 0, we're saying we're solving for an angle measure. Remember, cosine is restricted from 0 to pi. So when does cosine equal 0? So when does your x-coordinate equal 0? We would say at pi over 2. For part C, we have arc tan of root 3 equals theta. Again, we're saying, when does the tangent of theta equal the square root of 3? We're restricted, and remember, that would be at your pi over 3. And then part D, arc sine of 0.3. That's not an exact value, so that would be one where you're actually using your calculator. Make sure that you're in radian mode, and then you would do the inverse sine of 0.3, and you would get 0.305. Okay. Anytime that we're writing a decimal, we're going to round to 3 decimal places, unless it tells you otherwise. On the AP test, you always have to round to 3 decimal places. And then we have some properties of our trig functions. So when you take the sine of an inverse sine or the inverse sine of the sine, you would potentially simplify down to whatever you're taking that inverse sine or that sine of, as long as you're within that restricted domain to start. The same thing holds for your tangent, your secant, your cosecant, and all of those. So let's look at these. We're doing this without a calculator. And so if it's not a value that you know from your unit circle, you might need to draw a triangle. So for the first one, let's start with the inside, the arc cosine of root 2 over 2. So we're really saying, when does the cosine, or the cosine of what angle measure, equals root 2 over 2? And so we know the cosine is root 2 over 2 at pi over 4. So this question is really asking us for the tangent of pi over 4. And the tangent of pi over 4 is 1. So for the second one here, this is saying the sine of some angle measure is 5/13. That's what this middle inside part says. We don't know that, so this is where if you were to draw a right triangle, remember sine is opposite over hypotenuse. So our opposite side is 5, the hypotenuse is 13, and this question is really then saying, what is the cosine of theta? Because remember, when you're doing your inverse sine or your arc sine, you're solving for a theta. So if you used your Pythagorean theorem, you would find out that this side down here is 12, and the cosine of this triangle would be 12/13.